Hi, everyone. As Ricardo said, I'm Christine, and we're now entering the workflows and services block of talks. So I'm going to kick it off by talking about workflow tools, ones that we use on our systems here at ALCF. And I'll be doing some live demos. Be attempting that, but I'll be doing it on our machine Polaris. However, a lot of the scripts and recipes I'll be sharing today can be simply adapted to run on Aurora, and I've put pointers throughout the demo materials on how to do that. So I'm gonna stop my video and proceed. Oh, here we go. Okay, so let's get started. So we'll be talking about workflows. What is a workflow? What is a workflow tool? Why should you consider using one? So, for the purposes of the talk today, what I mean when I say a workflow tool is I'm referring to a piece of software that orchestrates the execution of large numbers of tasks on compute resources. And this tool should handle dependencies, data flows, errors, timeouts. Um, what can a workflow tool provide for you in your workload? Well, for some folks, if you just get to a point where you just have a very large number of tasks, this can be hard to manage at a human scale. You cannot do Q sub to PBS a million times. So bundling work into jobs is one thing that a workflow tool can do for you. If your workflow also has a lot of complex dependencies, like we're seeing this a lot now with simulation coupled to AI workloads, these tools can help manage these types of task dependencies. Um, it can also provide automation for things like error handling, restarts. We're going to hear about agentic workflows later on from Ricardo. Maybe you have an agent in the loop helping make decisions on the fly in an automated way. They can also provide elasticity. I guess I don't have that on this list, but if you have a single definition of a campaign and you know you need to spread it out over many jobs, these tools can actually submit jobs for you to the scheduler, and we'll see examples of that today. And the last thing I'll say is like it can also help you manage, either data movement or remote task execution. So we'll be talking a bit about that as well. So what we'll be covering today, and if you look up workflow tools, you will find there are quite literally hundreds. And so we obviously can't cover everything. So I'm going to focus today on two tools that are very commonly used on our systems, Parcel and Globus Compute. And they have somewhat different use cases and strengths. So we'll get a feel for that, and I'll be doing demos of these. Time permitting, I'm also going to talk about or try to demo a new tool that we've been experimenting with for the past year and a half on our systems called Dragon. This is a new tool being developed by HPE. And but you may not see your preferred workflow tool of choice here. If you need help getting started with a workflow and you already have a solution in mind, and you're struggling or you need help, please reach out to us. We're happy to help. And like I said, there's many tools out there. We can't be experts in everything, but we are experts on our machines. So we can help maybe bridge that gap between the tool you're using and our systems. Okay, so with that, I'm going to begin talking about the first tool we'll be demoing today called Parcel. Parcel is a parallel programming library for Python. So you can install this in a Python virtual environment or a Conda environment with pip. The way you create a Parcel workflow is you define something called apps. Now, apps are used to run tasks. So there's different types of apps. So there's one called Python apps, which run native Python code. And then there's also something called bash apps, which can call external compiled applications. Like if you're running, we'll see some examples of, you just have some C program you want to run many times. Um, the workflow for Parcel is contained within memory. So this can either exist on perhaps like a login node where you have some orchestration process there and it's submitting work to multiple batch jobs perhaps on your behalf. Or you can have the orchestration contained within a batch job that you submit to the scheduler. And we'll see both examples. Um, the workflow logic in the execution configuration are separate in Parcel. So we'll see this in a second, but essentially you create what's called a Parcel config that defines how workers are assigned to compute resources. And this can be swapped out machine to machine. So we're going to run in a bunch of examples with with a Polaris config, but you should be able to run the exact same examples swapping in an Aurora config when Aurora comes back up. And we have all those materials for you in the repo. Um, Parcel is built on top of a library called concurrent futures. And if you're unfamiliar with concurrent futures, it can take a little while to wrap your head around it. So I'm gonna just briefly describe what that is. So you have in Python these apps, which look just like normal Python functions. So you might think, okay, well, I'm running, I'm running this double function, for example, in the example here on the right. And, if I just call this in a normal script and it's just a normal Python function, D1 is executed first and then D2 is executed. However, with Parcel apps don't actually return the result directly. What they do is they return to you what's called a futures object. And the futures object is a proxy for the result that may or may not have yet returned. So what you can do in a Parcel workflow is you can create many of these futures and you can just do it all at once. So in this example here on the top with concurrent tasks, what happens under the hood if you do this with a Parcel app with this special decorator, and we'll see how this works in a second, these tasks don't execute sequentially. What happens is they get added to a queue that Parcel keeps track of, and they can execute concurrently if there are enough compute resources that Parcel is managing that can do so. And so in this way, you can, enable concurrent execution of many of these calls for this one with these applications. So you can also, for example, use the futures to chain tasks together by passing the result of one future to the next. And so essentially in all of these workflows we'll see with Parcel, the first step is you create the futures. And then you have to, at some point in your program, block on the result of the futures. And you want to make sure that you block on the result, and you do that by calling the future dot result. You want to make sure you do that in such a way that you get the execution pattern you desire. So in this case, on the top, you're executing these concurrently. In the bottom, you're executing them sequentially in a dependent way, such that you won't execute this future until you get the result from the future D first. So just wanted to lay that out. In working with users, sometimes this is a little bit of a sticking point in understanding how to run Parcel. So we are now going to transition to the demo portion for Parcel. So I have a shell on Polaris, and I have our code repository here, and we are in the workflow section. and we're in the parcel demo. And we have laid out here a whole sequence of exercises that you can run. We'll cover some of these, but not all of them, just because of time constraints. But we'll first start by setting up our environment. So if you are part of the ALCF training project group, which I think all of you should be if you've registered, you'll have access to this environment. So I've pre-staged it here. It has all the software needed for all the exercises in this session. However, if you do want to create your own environment, you can do so, and I have instructions on how to do that. So I'm going to just copy this and activate the environment here. Okay. And I have on Polaris, I have the repo as well. So I'll go to Parcel and we have all of the exercises. Excellent. So the first example is just very simple. So, and we're going to just run this on the login node. We're not going to try and run it on compute resources, just so we can have a sense of how this all works. So in a parcel workflow script, you'll have something that looks like this, where you import parcel, and then you might have defined within it your apps. You might import them from somewhere else. It depends on how you construct things. But in this case, we just have two apps that essentially do the same thing. And I'll just start this running. Where they both just say hello, but one does so with a Python app and one does so with a Bash app. So the executable executed by the Bash app is just an echo command. And you can see here, the result is returned to me at the command line. So how do you call these apps? Well, in a parcel workflow, you have to create your features within the context of a parcel config. So you can do that by creating a with block like this. So it says with parcel load. Here we're just loading the default parcel config, which executes tasks on local threads. So we're literally just running this on the login node, which is fine because we're just saying hello. And you can see here, we first create this Python app, but then we also append .result. So this will block until the result is returned. And here we do the same thing, but with the Bash app. Now, one distinction, Bash apps and Parcel, for a Python app, they return whatever the Python function returns. For a Bash app, it returns the return code of the executable. And so if you want to access the standard out of a Bash app, you have to write it to a file, which you can provide a path to in your app definition. And then you have to read it from the file system. So that's actually an important point, that for compiled executables, the only way you can kind of communicate between apps is you have to do it through the file system. Just though for the Bash apps, not for the Python apps. So I have here a number of examples that show different patterns of running, tasks. So you can do one where you run a bunch of tasks in parallel, tasks sequentially with dependencies, dynamic workflows where you have sub workflows, and you're free to look at these examples and test them out. But I'm going to try and focus on how, I was a bit vague on how you do this config, right? So in the previous scripts, you would see we just do parcel load and the default config. Now you can instead pass your own config object, and you want to pass one that is suited to the machine where you're running. So it would look something like this: parcel load Polaris config, for example. So in general, if you're running on an HPC system like Polaris or Aurora, your config will have several elements. Namely, you need an executor, which is the strategy that Parcel will use to stand up workers to execute tasks. You need something called the provider. How does Parcel get a hold of the resources? So are they just locally available, or does Parcel need to submit a job to PBS? And then the last is the launcher. How does it stand up the worker processes. In the examples today, we're going to just use something called the MPI exec launcher. So under the hood, Parcel will be using MPI to stand up these processes, but there's other approaches there. So in this case, this is an example, and actually, while I'm talking about this, I'm going to just submit exercise 4 to the scheduler. Hopefully that works. And I'll be basically running what I'm talking about here. So in this config, we assume that the resources are locally available. So you only want to use this config if your orchestration is contained within the job. So you use something called the local provider. Your launcher is the MPI exec launcher. So you're going to be standing up workers using MPI under the hood. And then your executor is the high throughput executor. And this is really good for cases where you want to run maybe one worker per GPU or one worker per core. And in this case, we're going to run one worker per GPU. So on Polaris, the way you can set that is you set how many workers per node or max workers per node, 4. We have 4 GPUs per node on Polaris. And then we set the number of available accelerators as well. So this tells Parcel that you want to use you want each worker to use GPUs. You can also set the CPU affinity binding for these workers, and there is like an optimal binding for GPUs on Polaris, and so that's what is detailed here. So in the script I just submitted, and I'll just show you what I just submitted to the scheduler, was just running this script here, hello in job orchestration. You can essentially define an app. Here we're just defining a Python app that will say hello from the host name and the GPU ID. And then within the context of the config we load, which in this case will be the Polaris config, but you can run it also on Aurora. There's an Aurora config here for you. You create a bunch of tasks. We created 20 tasks, and then we create them, and then we wait on them. So what that means is these can go off in the background and run on the workers, and then we collect the results as they complete. And so if we should have the standard out, hello Parcel output here. We can see here, excellent, we have the output of this workflow script here. And so in this case, you can see we have, we're just running on one node, so we're always saying hello from the same node. But then you can see we have different GPU IDs. So essentially, under the hood, Parcel is assigning the GPU affinity for the workers using CUDA visible devices. You don't have to set it. It does it for you. So you can also do this exact same workflow or work example, but instead submit it from a login node. And in that case, what you would do is you would use a different config, and instead of submitting it to the scheduler, you'd execute it as a Python task on the login node. So in that case, what you would need is you'd need a different provider. So this config is set up to run workers in basically the same way, 1 per GPU. But instead of the local provider, we set here the PBS Pro provider. And so you need to include in this all the information Parcel needs to essentially create the submit script for you. So you need to put in your account, the queue, scheduler options, all of these things. So I'm going to just start this going. Python 5. And it's going to hang, or it's going to look like it hangs for a minute. But what we should see, and it's running essentially the same example. Oh, here we go. So now we're getting output to us at the command line from these workers. And if we were to look at the scheduler, maybe my job's still there. No, it was too fast. But if we were to do it again, hopefully what you would see um, is that, yeah, Parcel has submitted to me for me a job to the scheduler to run the tasks and return to me the results. So if you have a campaign where you need to distribute work over many jobs, this might be a good option. However, you probably don't want to do it directly on the login node without doing anything else. We often recommend people start a screen session on the login node, and then you can run your workflow orchestration scripts and return to them at a later time, essentially. Um, so the last example here is running an MPI application, and you need a different config for this. Unfortunately, I'm not going to have time to cover that, but if you have any questions, feel free to reach out. And with that, I think what we will do is return to the presentation. So,
Christine,
mhm.
sorry, perhaps before moving on to the next tool, there's a question about
Mm,
parcel in
okay,
the chat.
sure.
The question is saying,
Could
I
you read
can
it
read
to
it.
me?
Yeah.
Yeah.
So I've seen that if I have 4 GPUs, but I define available accelerator equals to 8, parcel will not throw any error and will spin up 8 workers and start 8 tasks. How is that possible?
Um, so if you set max workers per node, it should always limit it to that, even if you set available accelerators, I think, to a larger number. Um, if that's not the case, the other thing I will mention, however, you can oversubscribe processes to GPUs, both on um, Polaris's A100s and Intel's PVC GPUs. On Polaris, it's using something called NVIDIA's multi-processing service. So I actually do have config examples of how to do that. So I'm not sure. Um, so I'm not sure exactly. So in general, if you set available accelerators to just like 8, it should in the background set CUDA visible devices to 0, 1, 2, all the way through to 7. Um, so if you set it to something that's not a valid ID, uh, yeah, I would have to know more. So maybe I can talk with that user
Yeah,
afterwards. Okay.
we could follow up. Thank you.
Yeah. Okay. So the next tool I was going to discuss is Globus Compute. So one thing to understand is Globus Compute is actually built on top of Parcel. So we're going to look at some config files for this, and it's going to look very familiar to what I just showed you. It'll be in a different format. It'll be YAML instead of a Python object, but a lot of the names are the same, and that's why. So essentially, what Globus Compute is, it is a task execution service provided by Globus, which you might be familiar with in the context of file transfers. And it runs on a, fire and forget model. So essentially what you can do is you can create what's called a compute endpoint on a target machine where you want to run workloads. And what you can do is then from somewhere else, and I'm going to demo running from my laptop, but you could do this from um, a machine at your university. You could do it from, another HPC system, which you might want to do maybe in the context of agentic workflows. You can submit tasks to this process sitting on a login node, essentially, on the target machine, and that process can submit jobs to the scheduler for you, kind of in the way we just saw with Parcel. In that case, I was kicking off the, process to start up the workflow, but you can also do kind of the same thing, but with this compute endpoint, which will just be a passive process in the background on the login node, basically communicating with the Globus service, waiting for work. And we have a lot of users from, say, experimental facilities like the APS, who use this to execute work for, experimental analysis. So they have a way of transferring files to Polaris, and then a Globus Compute endpoint stands up jobs for them that can then analyze that data as it comes in. So this demo will look a little different, but we're going to do it again on Polaris. So we're going to go to Globus Compute, and I will go. Okay, so in this example, we have these scripts. I'm actually not going to run them on Polaris. I'm going to run them on my laptop, and I'm going to show you that in a second. But first, we have to create an endpoint for us to target with these scripts. So that requires some setup on Polaris. Now, we've already loaded the environment, so we're not going to do that again. One thing you always want to note is the version of Python you are running on the compute side, essentially, because you need to have an alignment, at least in the major version. So in this case, that would be 3.11, with the Python environment you're sending work from, if that makes sense. And it'll make more sense in a minute why that is the case. But we have this all set up. We have our environment. Now, what we're going to do is we're going to use a config we have in our repository called polarisconfig.yaml to start to configure an endpoint and then to start the endpoint. So if you look at these options, it looks very similar to the Polaris the last Polaris example we looked at, where we were using a PBS Pro provider. We also had the same available accelerators and workers, the CPU affinity. All of these options are the same, and you can see here you have to oh, this is a mistake. This should be ALCF training. You need to have all the things that Globus Compute needs to write a job script and submit it to PBS on your behalf. So we have this, well, hopefully not exact config here, but oh yeah, we have the correct account and queue here. So what we're going to do is in our environment, we have a tool called Globus Compute Endpoint that was installed with the Globus Compute Endpoint package. And what we should be able to do is use that tool to first configure the endpoint with the config file we've created. And we have to also give the endpoint a name, and we're just going to call it workshop endpoint. So hopefully this works. Okay, so it says that I have configured it, and now I need to start it. And you do that by running Globus Compute Endpoint again, but you're going to start the endpoint this time. And it said, okay, starting endpoint. And you can always look at compute endpoint, the status of your endpoints with this list option. And so we can see the workshop endpoint is running. I have a bunch of endpoints for different projects and different reasons that are not running, but we have that one running. So, okay. So we have now, and actually, if you look under the hood, if you look at processes running under my username, you'll see this. This is the endpoint process running on this device, Polaris login node 2, that is communicating with the Globus service, waiting for work, but we've not yet sent it work. So what I'm going to do is switch to a shell that's on my laptop. And I hope this isn't too visually confusing, but this shell is on my local laptop. And I've pre-staged a Conda environment with all the software that's needed to run this step. Um, there are instructions here on how to install what you need to install in your local environment to replicate what I'm doing. But unfortunately, yeah, it's going to depend on your machine, your system. But I have an environment there, and I have again a copy of the workshop software. And great. So I also have it open in a VS Code base. So the first script we're going to run is remote adder. And so essentially, we define a function. It just adds two numbers. And we want to essentially send it to this endpoint for processing. So we have to give it the endpoint ID. And so when we created the endpoint, it gave us an endpoint ID. So you need to copy that, paste it in here. We can save that and we can run from my laptop, which is called Oberon, um, this remote function. And so essentially it says, okay, submitted tasks to remote endpoint, waiting for results. So it's very similar to what we were doing before with Parcel. Instead of opening a context with the Parcel config, we open a context with what's called an executor client. So that is pointing at the Globus endpoint. Now, the first time you do this, you will likely have be prompted at the command line where you submit the work from for authentication. And I guess I've been testing this out, so I already have authentication tokens stored locally. Oh, it returned. Oh, that's too fast. Okay, so but essentially, the first time you run this, you will be prompted for some authentication where you will have to, it'll give you a URL at the command line. You'll paste that into a web browser, and then it will bring you to our authentication page. And it's pretty self-explanatory what to do. But once you have that authenticated, you can submit to it. And here it's very similar. We create again a future, which is, you know, a proxy for the results of this function add func, which we pass to 5 and 10. And then we wait on the results in a very similar way. And so you can see here, it returned to me 15. And I guess it happened very quickly, but I still actually have the job going. So you can see here um, in our config, I think we set the timeout to like 5 minutes. So essentially this job will wait for another 5 minutes for work. And if it doesn't get anything, it will then shut itself down. That's a parameter you can set yourself. Now, this is just submitting a function yourself. However, you can also do what's called a function registration. So in this case, you can write a function, register it with the Globus service, and then you get what's called a function ID. And I'll do that here while I'm talking. And then you can use that function ID to run that function over and over again. And so you don't have to send the same code every time. So essentially we have here this to called registered function where we are essentially executing our function we just registered. And sorry, maybe I'm going too fast, but I'm pasting into this the endpoint ID I got for my new endpoint. And then here on the shell on my laptop, when I registered the function, it gave me again an ID for the function. So I just pasted that in here. So I can save that. And again, from my laptop, I can run this function, this registered function. And in this case, I didn't talk too much about what this register function does, but what it does is it uses Python's subprocess command to launch a compiled executable called Hello Affinity. It's from our Getting Started repo. It's just a C++ program that reports affinity, like the host name, GPU IDs, etc., of whatever device it's running on. And so this ran very fast, but if you scroll up to the top, you can see here it's it's submitted tasks and then it's reporting the results. And in this case, this function returns the return code of the application and then the standard out and standard error. And so you can see that here we have the return code, the standard out of Hello Affinity, which is just saying to Affinity and beyond, and then the host and cores and GPU devices, etc. And there's no standard error. You can also get information here in this script from about the task's execution. And so that's what I did at the bottom here. And that's what's printed here. And this returns you a record of the function execution. So it'll tell you things like the status. It will tell you things about the software used to run it. And then it will tell you, things about when it started, when it completed. So you can use this to get like performance information, things like that. So this is just a very simple example of how to use Globus Compute. And maybe I'll pause here. Ricardo, are there any questions?
There was a question, but Benoit was able to answer.
Awesome. Thank you, Benoit. And I will say Globus Compute is used in a number of the services that we're going to be talking about, especially the ones Benoit and Ditya will be talking about next. Um, you don't see it, but that's some of what they're using under the hood. So, okay, now let's see. I'm doing okay on time, actually. So the last tool I'm going to just sort of touch on is this is somewhat of a newer tool to the facility, but we've been talking with and working with HPE, the developer of this tool, for over a year now. And so we just wanted to advertise it more to users, and if people are interested in trying it out, we're happy to help out. So what it's called Dragon HPC. And what it is it's a distributed runtime for tasks and data movement. And that's kind of one of the key features of it. And I'll show you an example of that, of data movement in workflows. So this is a this is developed by HPE, which is Hewlett Packard Enterprises, which is also formerly known as Cray. And so they are the integrator for both Polaris and Aurora. They developed the Slingshot software that the network, how the nodes are networked on these machines, how they communicate. It's through software developed by them. So this is a new open source project just for executing tasks on HPC systems, but it's optimized to make use of the network expertise and software that HPE has and has developed over the years. So um, there's a number of there's sort of two main APIs. There's a Python API and a C API. There's a Fortran API in development. I'm not actually sure what the status of that is currently. Today, we're going to just focus mainly on the Python API because I think it has some interesting and useful features. One is Python is easy to use and easy to demo, but also the way they've developed this is that the Dragon Python API is an extension to Python's multiprocessing API. So if you're familiar with running multiprocessing pools, for example, in Python, they're trying to build on top of that API. And so I'll show you an example where usually with multiprocessing, you're confined to running tasks on a single node or a single, shared memory device, essentially. However, by just setting like one line, you can essentially run Python multiprocessing software or code pool essentially on multiple nodes. And that is, can be, is a very appealing feature. Um, I'll also say they offered something called a shard or a distributed dictionary, a sharded dictionary, where they create essentially memory pools on different nodes across the runtime that any process within the runtime can connect to. So you could have a process on one node, store something in the dictionary, and then have a process on another node retrieve that same information at a later time. And this is accomplished by Dragon establishing a set of manager processes under the hood in their runtime that does high-speed transfer of the data from memory to memory across the network. So this is a way of distributing data across a workflow without using the file system, which can, in some cases, be a bottleneck. Um, they have plans of creating interfaces for higher level workflow tools. I think they've already done that for SmartSim, which is also developed by HPE. They're also working on things for Parcel and Dask. And you can just install it with pip in a Python environment or a Conda environment. So let's see if I can go back to my demo, and I no longer need that shell. But I still need my shell on Polaris, and I no longer need this. Okay, so we are going to go up to workflows, Dragon. Okay, Dragon HPC. And then here we will go to Dragon. And I'm going to run these examples in an interactive session before we've been driving everything from the login node. So one thing about Dragon is it doesn't have the elastic capability that Parcel or Globes Compute has. You have to have everything contained within a job, a single job. So um, I'm going to get two nodes. Hopefully there are two nodes for me. Great. And I'm gonna go to, yes, this just takes me to the directory from which I submitted the job, which is where I want to be with all my scripts. Okay, again, we have a pre-staged environment. Using this -v actually brings that environment with me when I submit to the queue to get nodes, so I have that activated. And the first example we're going to look at is running a process pool with Dragon. And this is kind of included to just sort of show how things are simple to start with. So we have a script here, script 0, and I'm going to just start this running. Oh, okay. So one thing to note, when you run Dragon scripts, you need to run them with the Dragon tool, which will start the Dragon runtime. So it looks like a Python script. It is a Python script, but you start it with Dragon. Um, Now, what does this do? First, we define a test application or a test function, and this should look familiar. We were using the same one for our Parcel workflows. Essentially, it just says hello from a host and a GPU. Um, we then, in the main function, um, get some information about our allocation, like how many nodes we have available. Oh, wait, sorry, I should say back up. First, we set the start method to Dragon. So this is a tool within multiprocessing that allows you to set different backends to using the multiprocessing API. So we want to use Dragon, so we set that. Then we get some information about the runtime. We get information about the number of nodes specifically, because we're going to set the number of tasks and pool workers based on the number of nodes. And then in this first example, essentially we create a pool and we're literally loading multiprocessing pool here. But we have set the start method to Dragon. So then what happens, we then map asynchronously this function with a bunch of sleep times. They're all set to 1. These are the inputs. And then we get the results and then we print them out. So the results will tell us where these things were run. So if we go over here and look at our list of nodes, in a normal multiprocessing pool, they would all be running on the same host. But here you can see we have 2 hosts represented. So here you can see S37, S31. You have these node names that have to do with things about the racks and the blades and things. But essentially you can see all these pool, all these functions were run on processes on different nodes within this pool. Now, the one thing is there's no setting for GPU affinity here. So essentially all these processes, we're running 4 processes per node, essentially, but it doesn't know how to select GPUs. So then we have to go a little bit beyond the straight up vanilla multiprocessing API. So now instead we use the Dragon native pool, which I import here, Dragon native pool, import pool, as I've called it here, Dragon pool to distinguish it. Now, with this implementation of pool, this has a different API from the standard multiprocessing. So if all you care about is running a bunch of tasks across different nodes, you don't care about GPU affinity, or maybe you have a different way of handling GPU affinity, this might be sufficient. And if you have scripts that you can just extend with start method Dragon, that might be great for you. If you need finer control, this is like one level up where you can pass to the Dragon pool a list of policies. And here we just grab a very simple list of policies. This gives us, so a policy, sorry, I should back up. A Dragon policy is a rule for where and how a process will run. So you can tell the policy may include things like the host name, the GPU, the cores, things like that. In this case, we get a list of policies, this system.gpu policies. We'll just grab a set of policies that has 1 policy per GPU in the runtime. So this is just a very simple way of extending this, and then we can set how many processes we want to run per policy. And we'll just do 1 here. Then it looks basically the same. We use the same map async command and get the results. But this time you can see we've actually selected specific GPUs for each process. So, and that is being determined by the policy that is being used for the worker that ran that task. So this is just a very simple description. There is more ways of doing fine-grained control of task policy and execution. There's something in Dragon called a process group. And if you're interested, this is a simple example, kind of running the same application again, but in a different way, where you can set policies that include node names, CPU affinities, and you can have more fine-grained control. The last thing I want to say about Dragon, though, is point out the dictionary functionality, because I mentioned that early on, and I just want to show an example here. So this example, script 3, and I'll just start that going. What this does is it again creates a multiprocessing pool, but we give it essentially an initializer that attaches it to a Dragon dictionary. Here we create the dictionary object, and to create one, you have to tell it certain things. You have to tell it how many manager processes you want on each node. That determines like how things about how data is like moved. So essentially the managers control the movement of data. So you set how many managers you want. You set how many nodes you want, say in the dictionary spans, and then the total memory across all the nodes. So we just set 1 GB per node. Um, and oh, how do I scroll back? Here we go. So we create the dictionary and then we can pass it to the pool initializer so that so pool processes can attach to it. And in this example, we then run in this pool this assign function, which essentially loads data into the dictionary. So data is loaded into the dictionary much like you would use a normal Python dictionary. You just have a key and a key value, and this is what it looks like. So essentially, across my two nodes in this allocation, we have both nodes adding things to the dictionary, okay? But then at the end of the script, we have this orchestration process, the driver process, pulling data from the dictionary. But some of that data is going to be on the local node, but some of it's going to be on the other node. And under the hood, it is these manager processes that are doing this data distribution. So I just wanted to highlight that. Okay, and I am reaching the end of my time. Um, there are a lot of tools, workflow tools at the facility in the world. Um, these were just demos of a few. I do want to mention we have one tool called Balsam that has a long history at the facility and is still used and still supported. So I did want to mention it. This is a tool that's really optimized for running large ensembles of MPI applications. And it works on a database model, which is a bit different from all the tools we were just showing you. Most of the tools we showed you today, the workflow exists within memory of some kind of orchestration process. With Balsam, there is a database that lives on a server within Argonne that you have to get access to the server. So if you want access, feel free to email and we can add you. And so essentially, the database keeps track of the status of tasks that you add to it. And Balsam works like Parcel in that it will submit jobs to the scheduler on your behalf. So it's also has a Python API, so you describe your applications in a Python class, and then there's a command line tool that allows you to track the state of tasks within your portion of the database, which is called a site. So I did want to just mention that because we have had questions about whether Balsam is still being supported, and it is. So, we're happy to give any pointers on Balsam if you're interested. So with that, I think maybe I'll conclude here. There's a lot of tools, like I said. Obviously these slides will be provided to you and you have all the exercises in the repo. We regret not being able to demo all of this on Aurora, but I've tried to do my best to point out where you can make a change and run these examples on Aurora. All of them should run there as well as on Polaris. So with that, I will conclude and take any further questions you may have. Thank you.